hour of solar radiation power on the Earth is 1 year of our human beings' consumption. So, for solar cell technology, there are you can categorize them into different generations. There, the first generation is silicon-based solar cell, which is still the dominant technology in the world. And for making that, you will have the processes from the sand to crystal growth and etc. You go through this cutting, making the p-n junction, etc. To make the solar cells here. Second generation goes with the thin film solar cells, and the third generation, which are the main topics of the research nowadays, including organic solar cells and perovskite solar cells, and also the dye-sensitized and quantum dot solar cells for some less extent. The key point of doing this part of the research for me coming from the dream of going for the printing solar cells. This is actually when I worked in organic solar cells, that's the row-to-row pilot line that we built in a small company. Okay, so what is essential for solar cells? Well, we might just make it simple as said that you need a good semiconductors, absorbing light, transport, etc., carrier mobility, and you also need interfaces there. And for the so-called hole contact, you will want this one to have your holes to be transported well, while you block the electrons to go this direction. Same thing happens for the electron contact. You want the electrons to be able to generated to be able to go to your electron electrode to be smoothly, while you block the holes transport there. Okay. So in this talk, I will mainly focus on the semiconductor part, assuming in fact that lots of work has been done to on the interface to make sure that we can have good contacts there. So part one, let's go to the organic solar cells here. Organic semiconductor materials, it's a semiconducting material, and the semiconducting coming from different ways as the inorganic semiconductor. For the organic semiconducting materials, that they will have so-called alternative single and double bond. Single bond, double bonds, and this long chain single and double bonds will allow you to have the delocalized pi electrons. Okay, and they have the pz orbitals. These electron clouds can share. Okay, can share. So it's delocalized. Then you have the property of the semiconducting properties there. And you can mimic this one in organic semiconductors. The proper way to call them is HOMO, highest occupied molecular orbital, and LUMO, that's lowest unoccupied molecular orbital. But if you want to link this one to inorganic semiconductor, you might think about that one as this one is conduction band minimum, and then this valence band maximum. Okay. But remember that organic semiconductors, they are more of a molecular property rather than this band property there. This one is the bottom one shows some of the progress of organic semiconductors there. This is coming from a review article we wrote in 3 years ago, and about the important parts that, for example, you have the bilayer organic solar cell reported in 1986, and in about 1995, you have the invention of an important electron acceptor PCBM, and bulk heterojunction concept, etc. Okay, with many years to go. And after that, we have this more latest. We have this non-fluorine acceptors, and that one happens in 2015 and go on. And nowadays, that's the ITIC series and the so-called Y series non-fluorine acceptors really give a huge boost. Then we have the efficiency goes to 16%, 17, 18, etc. Okay, it's a very exciting time. Okay, for the polymer solar cells working principle, I just copy the images that's for 2012 review article we wrote. It's a simple one. If you are from a layman want to understand that one, it's probably a simple one to read. And the working principle is you absorb the photons and you will generate the so-called electron hole pairs. And the second step, electrons will get diffused into the interface of so-called donor and acceptor interface, where the excitons, which is the electron hole pair, will be separated, and then electrons will transport to the cathode, and holes will be transported in the donor to go to the anode. Okay, so that's form a loop and generate from the photon to generate the electrons there. And for organic solar cells, their morphology is an important part. And here shows what people image of the cartoons for the organic solar cell morphology. You want an interpenetrating network of the donors and acceptors. Each have their pathway. Okay, and they want the domain size to be not too big. Because your excitons need to go to the donor acceptor interface. Okay. And we have another review article 2 years ago that's on the non-fluorine acceptors. That's if you are interested in that part, you can find the information of the wide band gap, so-called media band gap, and also narrow band gap non-fluorine acceptors. That's exciting topics there. Okay, so I want to get some brief introduction of the work here. So semiconducting active layer for organic PV, you will need a donor and acceptor. Two names I want to mention very strongly that they are pioneers. Professor Qing Tang now in Hong Kong, he invented the bilayer organic solar cells there. And Professor Alan Hager got the Nobel Prize in 2000 in chemistry. That he's the one that invented the bulk heterojunction. And in 1995, Cambridge Professor Richard Friend's group also contributed to the bulk heterojunction with polymer donor polymer acceptors. Well, the material here are invented in really early. Okay, and it's actually take more than 10 years for people to realize how to get a good morphology for these materials to get a reasonably good efficiency, and that part including thermal annealing method, and the solvent annealing method, and additives or mixed solvent method. These are, if you think about it, these are the methods that actually propagate until today, that influence the research here. Okay. Now I want to mention very briefly on the morphology. For generation 1, that's a P3T PCBM. These are the polymers that for this type of the polymers, that it's around 2005 that people realize this morphology. That's a polymer donor. You'll see the fibril structures with the width about like 20 to 30 nanometers wide. And that gives you a direct hint of say, okay, I assume the morphology should look like, and this give us the evidence that, in quote, a relatively good polymer solar cells, what it looks like. Okay. And it's also slightly later that we are able to use the so-called grazing incident XRD technique to identify what are the molecular packing for these polymers. And here is what we see. These are so-called adjunct orientation, and this tells us this within this polymer blend, this is the polymers are aligned this way. Okay, aligned this way. This is from bottom, you transport to the top. Okay, so that's give us the hint of one example of how do you get a good morphology for solar cells there. Okay, and this works that done in Professor Yang lab in UCLA, getting good citations there. Okay, thanks to the researchers globally. Okay. In fact, I was able to check something about Nature Materials. Then 2 years ago, we found that this paper was actually ranked number 5 within all the papers published in Nature Materials there. And number 6 is actually another solar cell, that's nanowire dye-synthesized solar cell. That's from the Berkeley, UC Berkeley, Professor Pei Dongyang's group. You'll see that well, it's probably coincident in that period that solar cell, new type of solar cell gets lots of attentions there. Okay. Personally, I also involved in second generation of polymer solar cells there that we worked with. I was in a company, leading the company, and worked with Professor Luping Yu. And we have a very smart chemist that's both in Chicago and in our company that we are able to publish several things. Then here is a 7.4% efficiency, and then slightly later we get the Nature Photonics paper, which is getting you about 7.7, and later get 8% efficiency. Okay, so these polymers, they get a lower band gap. Okay, so that's band gap from polysilicon from 1.9 eV, and this one goes to 1.6 eV. Okay, so absorbed more and still get a good quantum efficiency. We get really excited about it. Okay, while this is things that people go for getting excited on efficiency, that we do have people like it, and this advanced material paper is actually is also another top 10 paper in the history of advanced material. And for the Nature Photonics paper, and that one was ranked number 5, and for the research article, and well, the simple review article is actually also getting good citations there. Okay. Then, well, for me, that's the reason to mention this one coming from here. So we have the bulk heterojunction OPVs, okay, and we found that the generation 1 and the generation 2, they all give you good quantum efficiency, but they actually have very different molecular packings here. And here is so-called adjunct, and this is phase on. Okay, and this one actually influenced my research. That after going to Hong Kong too. Okay, so later that we did something that in UCLA developed this lower band gap polymer donor. And we can pushing the things to go beyond the 1.4 eV band gap. Okay. And why this one is important is that if you think about it, about the tandem inorganic semiconductors, you can have one subcell which actually at 1.4 EV band gap. Okay, so that opens a broad view that you can do many things. In fact, we also use this one to go for tandem polymer solar cells, which are will not be talked here. Yeah. Okay. Also note here is for this thing, we also see this polymer is so-called face-on orientation. Okay, similar to the second generation. Okay. Now, with the materials with different band gap, that's a 1.9, 1.6, 1.4, and we can actually think about how can we getting things working them together. In addition to what you get a tandem solar cell, we know that's the way that you can overcome so-called shock equalizer limitation for single junction. Well, can we do things that combine these materials with different band gaps? Considering you really have a narrow absorption band, can we combine you guys and getting higher performance? And that's really one of the topics we do on the so-called multiple donor polymer OPV as the first try. Okay. So what we choose there, if you see, you have P3T and this band gap 1.4 solid material. You think they have a good match. Then we say, okay, let's put them together and see what it looks like. Okay. Well, although the band gap matches pretty well, absorption, the 3.8 for the polysilicon and 6.3 for the low band gap polymer. When we try hard, we cannot really get good ternary device there. Well, we get frustrated and think about what's going on there. And this part of the quantum efficiency tells us something. You can have polysilicon EQE this way, lower band gap this way, but when you put them together, they are not adding up, but rather they go down directly. Okay, so we think the method might come from the fact that one of them is so-called edge-on orientation. The other one is so-called face-on orientation. When you're putting them together, your whole transport should definitely get something worse. Okay, so if that's the case, we will then we can try things that have a similar molecular packing, and so that comes this PTB7 and this lower band gap. Both of them have a face-on orientation, and indeed that we optimize the device. We were able to starting from this 7% and 6.7%, these two port, and putting them together, we can get a higher performance, which goes 8.7% efficiency. So that tells us, well, device is getting good. And what happens that from the XRD, grazing incident XRD evidence. And here it is. We have P3T. This is a wider band gap, and we have this mid band gap. This PTB type. These are just the top one and the bottom one are just. This is good but not best, and this is best. Similar, good, and this is the best one. Okay, so we see that if this is a face-on orientation plus edge-on orientation, we cannot find this face-on orientation anymore, which tells us this low band gap polymers packing was severely destroyed there. Okay, and but if you go with this both face-on orientation and in this ternary devices, we keep the ternary things packing pretty well, and this give us hints that in morphology wisely they get less traps there. So by that way we can retain the face-on orientation. Well, here we if you do not compatible, they do not give you a good orientation. Okay, with that we propose a scenario that this is morphological traps that will be strongly related to your molecular packing and how do you orientation of it. Okay, so so that's before I came to Hong Kong. Okay, and came to Hong Kong. we continue the research to see that how can we optimize morphology for multiple component solar cells there. And here is one that we get this one's we change it to small molecule, all small molecule. And my collaborator, Professor Shirong Lu in Chongqing, has lots of experience in this liquid crystal BTR. And they synthesized another one, BTR-OH. You put in this some OH groups there. And well, structure-wise, the compatibility is not an issue, and we tried to optimize in the ternary system. Okay, and this is energy levels here. Okay, well, everything band gap looks similar. We were able to get a higher performance here. We start with the BTR as the orange one, and the ternary we can push it to higher current and higher fill factor. And higher current can be seen from the EQE, and we do have a more efficient exciton dissociation and charge collection. The system shows that ternary will allow us to have to eliminate the bimolecular recombination and also have less traps here. Okay, so that's fall into the same scenario that you're using the molecular compatibility. We will be able to tune the morphology for the ternary system. And for device-wisely, we get from 9% to 8% for each of the binary, and we can get 10% in the ternary here. Well, beyond what we are talking about, the molecular packing structure similarity and the packing, and this work also indicates some crystallization tuning as a new parameter that you can use for optimize the ternary OPV's morphology. And what you show here is this. So we have this one is a BTR, the highly crystalline, and this OH. This OH is the one that have a less crystallinity. When we tune them morphology, we will be able to get a crystallinity in the intermediate phase, okay, in the intermediate level, which tells us is that the crystallinity and the domain size are important parameters for getting efficient solar cells morphology. Therefore, this way is a new parameter we can use to tune the morphology here. Okay. And the system, ternary system can also go to seeker film, which as we know that we want to printing, this is a very important part for larger area getting good film, okay, without short. Okay. Okay, so that's all on fullerene acceptors here. We know that polymer solar cell are getting a lot of attention. And in 2016, the year that I moved to Hong Kong, and here is the top 10 research front in chemistry and material science. So that's number one is the non-polymer acceptor organic solar cell, and number 6 is you see the emerging of perovskite solar cells here. Okay. In Hong Kong, we worked with non-fluorine acceptors too. The way that we step into this area is we're thinking about, okay, you have a wider band gap polymer donor and you have low band gap acceptors there. Okay, so how about I get you thinking about how can I get in probably VOC better, and also the matching of the spectrum. So the way that the project I want my postdoc to do is design wide bandgap polymers, but I want you to have a deeper HOMO. Okay, deeper HOMO will help you, will at least do not reduce the ternary polymer solar cells VOC. And here are 2 works that I want to talk about in the past 2 years. This is a general slides for getting design a DA donor acceptor moiety to tune the to tune the energy level and the band gap and the energy level, and of course the transport properties too. And using donor unit, acceptor unit, and you can also select the so-called quinoid structure to reduce the band gap, etc. Okay. In this work, in Hong Kong, this is coming from the molecular design and assisted by the density function theory calculation. What we design here is in the former PTB, etc. Star polymers, you use BDT unit, which is sulfine, benzene, and sulfine. Okay, we extend it more. Okay, extend it more. So you still have the similarity of the planarity. Well, at the same time, you can tune the properties there. Okay, so these are the two molecules here. We use relatively weak electron donating capability and the electron withdrawing capability of these moieties to tune the energy level, and we use the DFT method to simulate whether our design methodology sounds or not. Okay, so we find that these two molecules will have a comparable molecular orbital energy levels, but they have a different dihydro angle, so that can find out that the molecules here that D, the second one, will have a better planarity and also a redshifted absorption. And that can be seen from here. This is dot D. That's a redshift / smaller band gap. And for the devices we make, the backbone system, star system, is this PBDB-TSF. This is a black one, and acceptor the IT4F here. Okay, and we have this our two polymers, new polymers, to be on the left here. Okay. The band gap are like about 2.0 EV. Okay, and for devices, let me get a quick for the devices here. We see that compared to the classical donor, this one, we get a deeper homos here. That's exactly what we want. We also have wider band gaps there. But remember, these two are still not as deep as the acceptors here. Okay. For device data, this wider band gap have higher VOC, but poor performance. But when we put in that 5% of this polymers as additive, we are able to improve the efficiency here. Okay, so overall, that we have the baseline to be about 12, and we are able to improve that one into 13% efficiency. Okay, so that's the first successful try that we have done in the molecular design and for ternary solar cells here. Okay. And we further try an even deeper HOMO level polymer acceptor. And this is the molecular structure here. Well, now we go back to this BDT here. Okay, but this one was designed so that you have a deeper HOMO. It's actually even deeper than your acceptors here. Right? Well, people turn not to do that because they are afraid that if you are even deeper than your acceptors HOMO level, how about it becomes a whole traps here, right? Yeah, well, we are curious about that one too, and we think, well, maybe you can do this thing with a smaller amount without disturbing it too much. Is that the case? Okay. Here is what we see using the this classical system, still like this one and IT4F. Okay, and we find that for this for adding smaller amount of it, we go from this black curve to this red curve. Yes, okay, it's release your stress using, well, adding this deep HOMO material actually do not form the traps there. Okay. This part, like a general characterization, I'll pass it. Okay. Let's go direct to the performance here for two systems. For this material system, if it is binary, we get 11.9, and we're adding 5%. We can improve that one to 13.1% efficiency. Okay. And you're adding more. You'll see the VOC is increased there, but the efficiency not that good anymore. Okay, but that's okay. So we have additive, get a smaller amount. We try another system, which is PBDP-T and ITM. Well, anyways, another quote star system there. You can see the efficiency can also be improved from 10.3 to 11%. Okay. Nowadays that we go for polymer solar cells, and we try this so-called Y series here. Okay, great work that's from Hunan. Okay, so that we try this system, which are giving you about 15.7% by Professor Yingping Zhou in the published on JAR last year, and we found that this strategy we can still improve our devices from 15.4% to 16.3%. That tells us that the hard work that we do in making wide bandgap polymer do not waste. And also that we can, when this system getting thicker and thicker, we see the efficiency have a mild drop. Okay, goes to 300 nanometer. It's still pretty good. Okay. More excitingly is probably on the stability. We see that we see here. Okay, this under the light, if the binary after 500 hours, it drops a lot. Okay, well, in alternary, although we only put a small amount of the polymer, we actually get a much better stability. Okay. Okay. Let me move to second part of perovskite solar cells there. Okay. Well, we don't need to go much detail. It's a phenomenal progress. We know that efficiency now goes 25.5, and more importantly, it can be low cost. And for me, I like the printability. Okay. So for molecular structure, this is a ABX3 structure, and where A is can be this type, and B is those lead or the tin irons there, and X is the iodine, bromine, or chloride. Okay, so these are mixed perovskite, organic, inorganic, mixed halide perovskite. So for land map, compared to silicon, which is have a high efficiency, now goes to 27%. Perovskite is slightly lower, but improve the most. Perovskite cost is an advantage, but the stability is a critical issue we need to solve. Okay. So my research is also going with that one. There is intrinsic instability, like moisture, oxygen, etc., and there is intrinsic instability. This includes phase instability in some type of the perovskite, like the FAPBI3, and this is all inorganic perovskite too. Okay, and that's also including its stress, the strain related instability. So for my part of the research, starting with the organic solar cell, we want to use the non-fluorine acceptors. One part in our OPV research, a second part can we use that one to improve the perovskite. So that's the topics that I do for our researcher. So this is things that we want to do. So in organic, in perovskite solar cells, anti-solvent at that time, 2016, 2015, is anti-solvent. It becomes a very, the star method. It's using that one to improve the getting very good morphology and high efficiency. Okay. What you do is during the perovskite spin coating, in the last part, you drop some chlorobenzene organic solvents onto it. Okay, so we say, wow, since our non-fluorine acceptor molecule can be putting into it, and we do that, let's see what happens there. So by doing this way, instead of pure chlorobenzene, you're putting those non-fluorine acceptors, you will be able to penetrate into the green boundary on the top part. Okay, so and we are also considering this carbon-oxygen double bond, and hopefully that one can passivate the green boundary and reduce traps in perovskite. And here is what we get. Okay, this is XRD, not much different, and absorption not much. But for devices, we are able to control the amount of the non-fluorine acceptors to get higher efficiency. At like 0.2 milligram per milliliter, we are able to see a VOC increase and also the fill factor increase. The efficiency was able to go above 20%, and we get really excited about it. Well, 81% of fill factor. Wow, that's a great value to have. Okay, so that's this is small work that give us confidence of applying organic semiconductors into the solar cell research, perovskite solar cell research as an entry. Well, stability is a big issue, and we want to not only passivate the traps, but we want to protect the perovskite because this one dissolve in water. So the second one is we use this star polymer in OPV, and we do the same trick so that we can apply that one on top of the perovskite using the anti-solvent method. Well, it can dissolve in the organic solvent anyway. So this is device structure. You start with FTO, and then you have a tin oxide. We use that one as an ETL, electron transport layer. And on top, we build our perovskite formation, of course, assisted by this anti-solvent with polymers there. Okay, and then standard spiral whole transport layer and electrode there. And go directly to device performance. Yes, in the proper amount adding, you get from here to the red one to the green one, which is 1 milligram per milliliter polymers there. This gives you the highest efficiency. When you're adding things more, okay, it goes back. Okay. Well, it's not surprising because we don't expect to have too much polymers as the mobility is not that high. Okay. So in short, that we are able to get this is 19.9% efficiency. For the method, for the principle, we use this Raman spectra to identify what happens there. Okay, so what we see here, we monitoring this peak about 70, and this peak 143, which it shows the lead and oxygen stretching mode. And from there, we see from the increase of that one, we see the evidence that the lead and the oxygen, the iron and the oxygen can form so-called Lewis adduct. So this coordination passivate the traps and making the devices less trap and higher efficiency. So that's on the efficiency side. So we do statistical distribution, and we can clearly see the improvement about 2% efficiency. Also, we store this one in dry air, okay, ambient air, but the lower humidity, about like 6 months there, you'll still have a really good performance for the polymer passivated one. To me, that's actually more interesting part is actually on stability on water, against the water. And here you'll see that we do add a little bit of polymers there. Then we see that if there is no polymer in the anti-solvent, when you drop a water, immediately you actually becomes yellow. That tells you the perovskite photoactive layer decompose. Okay. Well, if I'm adding 1.0, which is the highest efficiency system, we see that we can drop this one for 1 minute, 5 minutes, 10 minutes. It's still not totally as bad as here yet. Okay. So that tells you this polymer does give you a dense protection of the green boundary to help protect your device. Remember, this 2.0 are slightly more, and this one getting you a slightly lower efficiency, but if you take a look of the water protection property, it's amazingly good. Okay, so this is a useful method for you to protect your perovskite film and protect the device. So that's exciting. Okay, I'm going to the second part of my perovskite one. Okay, so we play with efficiency, and then in my mind it's always keeping in mind, say, can we do printing perovskite solar cell? I have been done organic solar cells printing, and this is what we do in the company in South California, that we can make. This is one piece is about 15 centimeter by 15 centimeter, and we can make a sub module, and these modules can be putting together and make a big modules there. We actually putting this thing on top of this movable house next to the silicon modules there, and to have some testing. Okay. At the same time, this is the row-to-row testing pilot system that's about polymer strap coating. Well, thinking about the way that we do here, we'll find that, well, the way that we do for the anti-solvent dripping process, you need to control exactly very narrow window, when do you drop it, etc. And it's a spin coating, and that one can very hardly, if possible, to transfer it into large area coatings there. So that's why second part of the research for me goes to this blade coating. Okay, this blade coating, we want to use blade coating to coat large area film. At the same time, I want to use air knife. Okay, what we show is air knife to study the dynamic kinetics of the drying kinetics there. Okay. I show it this one is horizontal. That's because this one helped me to do the so-called in situ study there. Okay. And the air knife is good. It's a low cost. If you think about that, so we can, dry your lovely, tastily cherries, then you know this is a good one to use, and it's linked to low cost fabrication. Okay, so first that we use this so-called in situ UVVs apparatus. So that one will allows me to see what happens of the drying process of this perovskite. Okay, and the intermediate films can take a look what happens. The first we do so-called natural drying film, and we find that we get a film coated and let it in the glow box and let it dry. And you'll see that depends on your parameter. Well, we will see this a very wide window. Okay, we have a very wide. It's a little bit slow. Okay, very wide window so that we will be able to, nothing changes in the liquid phase. And in the middle, you have the intermediate phase in the green part. And when you, after that, this 800, 900 seconds, you'll see the stabilize. Okay. So, this, during the windows there, you will be able to see, you can do air knife quenching, faster drying, then we will able to see the red curves here. Okay. Computer is slow, sorry for that. Okay. I can start about 40 seconds, start to air knife quenching, and we have a much faster drying speed. And then on the D, on part D, you will see this red curves here. The magnitude widely is about 2 orders higher drying speed. And for the natural dry, this is what you have. You have a perovskite, a big trunk of perovskite. And next to this perovskite, you already see this FTO, this electrode, which is not good. Okay. And but in the air quenched one, we are able to get a smooth morphology. Okay, smooth morphology. Okay, so that's exciting. Okay. So this one, I would just say that you have what happens on the left, what happens on the natural dry, and what happens in the intermediate phase. You start to have some perovskite aggregates already, but if at that time you start to do air knife quenching, you basically can lock it. You will see the perovskite big chunks there, but the other part will be fine. Okay, so that's an intermediate phase. Okay, well, in intermediate situations there. Okay. So no much words about that one. For the part, as long as you are in the liquid phase from 0 to like 14 minutes, and we show that this is 0 and 12 minutes, I start to air knife blowing. We see the films that we get are actually very similar. And this is XRD, you can see it, and you can see the efficiency, this correlation length for your perovskite film, okay? And overall, you can get the device basically the same, okay? And when it goes to 18 minutes, which is already in the middle transform zone, that's efficiency, where efficiency starts to drop. Okay. So we do have a wide window for you to get, and we know where are the critical points you need to consider. Okay. So go to the device. A few informations here. We will be able to get a different starting time. This, as long as you are in that liquid window, you get similar. And the intermediate 18 minutes, you still have it. But natural dry, this is too rough and get lots of short. You cannot get anything. So that's for device efficiency. This is a statistical data there. Okay, that's what it shows. And this method can handle different thickness of perovskite from 160 to like 1100 nanometer. That's sometimes you require it for higher quality coating in large area. Okay, for mechanics, for mechanisms there, we propose this one. So if you are doing air knife quenching, you will be able to get quickly shoot over this so-called minimum super saturation limit. Okay, if you over it, you will quickly get a lot of nucleations there. For the natural dry, you dry slowly, and when you over it, you will nucleate, but then you go down. So they'll have less nucleates there. Okay, so we see that nucleation rate and the cluster size of the perovskite nucleates are, comparable to each other. Okay? But overall, take-home message is you can use a fast air quenching method to build a high-quality perovskite, which have a quick nucleation and lots of nucleations, and then you grow and getting them to have higher quality films there. And the bottom one, D shows this natural dry perovskite after annealing. You see it's a big chunk. Okay, and this one is the air knife method that we can get a uniform and high photoluminescence indicates you have a good high quality perovskite film. Okay. In summary, for this part, that we are able to get a hysteresis-free perovskite device using the simple air knife helped method. So to get a 20% efficiency, and we're able to, on the larger area, to that's 1 centimeter square, we get over 18% efficiency. Okay. So that's what we do in Globox, and we do a second work that we try to do it in the ambient air. Okay. This one I would call it that's facing to the future for the manufacturer friendly ambient air fabrication. Well, the reason is this: in Globox, that's what we see. Okay, but if I'm doing it in air, we coat it in air. This is what we observe. Okay, although the scale are different, but you can see this part, the morphology or the natural drying of this perovskite have a very different form as the air glow part, and that one is linked to the moisture in the air. In fact, if you think about this one, this is now the winter. You go see the window in the north part of China. You can see those beautiful ice flower, and you can see the similarity of what this one here and the ice flower. Okay. So in this work, let me give a brief thing that we are able to use air knife method to get a 21% hysteresis-free perovskite. Okay, and at a humidity with relatively high, about 55%. Okay. And here is the apparatus diagram, and what this work compared to the other people's reported work here. Okay. Okay, here is the equations here. And we find that in ambient air and in Globox, if I'm fast enough for the drying, they actually looks very similar. Okay, looks very similar there. Okay, and for different speed, that's 40 milligram per meter per second versus 28. The efficiency actually can vary quite a bit. Okay, you see a efficiency for that for about 5% versus 0.3. Okay, so in ambient fabrication, yes, remember that we do need the air knife to be fast enough to remove the solvent to help you to get a good efficiency here. Okay. Device-wisely, we get 21% efficiency for small area, 6 millimeter square, and we get 18% for 1 centimeter square perovskite device. That's shown here. Okay, and the slides here shows that in ambient condition, the blow rate play a significant role here. The devices, although I'm fabricating this one in high humidity, 55%, we actually see the stability of this device is actually good if I'm using fast enough blowing. Assume that when we're doing that nitrogen blow, you actually avoid the water to penetrate into destroy your device. And this one, the blue is air, this is in glow box, and the red one is in the ambient air fabrication. We see we can achieve similar performance, but of course the red one will give you much lower cost there. And this method actually can give you over 65%. It still give you a pretty good efficiency here. Okay. Okay, this is the last part. I know I don't have quite a bit too much time, but I want to mention this briefly that those two works that mainly just for that air knife blow. Okay, we'll try to avoid the anti-solvent method, which is not good for fabrication. And this method, we try to address both coatability and also stability, and also manufacturability, stability, and efficiency. What we pick here is this: we still keep the apparatus. We are adding functionality. Okay, we're using this zwitter ionic surfactant. It's a surfactant with a long chain. This is to help you to do coating. Okay, and we want to do it in the room temperature. That's always our part of the work. Okay, and this molecule, it has both positive charge and negative charge, and that will help us to passivate the charge, the defects there. Okay. And this sulfur oxygen double bond will help us to do the passivation. Okay. This one has this long chain is don't like water, and this part likes water. Okay, so this will gives you some protection of my device too. So that's what we call the multifunctional there. Okay, now this is the so-called time of flight sinks. Okay, this tells us where are these surfactants are. Okay, then we can see that it's actually close to the surface. Okay, they like to be on the surface of my perovskite film. But at the bottom, you still have another enhancement there. That's agrees with the scenario that we'll have the long chains there to be pointing outside on top and point downwards. Okay, so that tells you it can actually protect your perovskite on both top and bottom, although at different degrees there. Okay. Okay, so we use so-called inverted structure, which at the bottom we start using a polymer PTAA. And that one is not good for coating if you do not do anything. And this is shows if I just using perovskite solution coat on it, you know the quality is not good. And SEM, you see pinholes there. Okay, section you'll see that's voids there, tells you contact not good. When we put in these surfactants there, functional surfactants, we have very good coating uniformity and no pinhole, no pinholes here, and contact wisely at the perovskite and the PTAA, the contact is very good. It's very good. And we also want to point out that you see the contact angle, the perovskite ink on top of PTAA. This one is without surfactant is big, and become smaller and smaller when the amount of surfactant increases there. And according to this Gibbs free energy for this heterogeneous nucleation, then we can see that when you're getting the contact angle small, you get better coverage and better film formations there. Yeah, we did something on the in situ crystallization. Then a few things there. First, that we were able to have access to Taiwan's synchrotron source to study the intermediate phase. And what we found without the surfactant and with surfactant, what we see that the new with our surfactant, functional surfactant, we see new adapt. In other words, that's intermediate state. And this surfactant with the SO3 then have a stronger coordination with lead, and that tells that was able to tell us that when you do the nucleation, it's starting faster. Okay, we actually. If no, it starts 21 seconds. If it's having the surfactant, it starts about 11 seconds. So it's getting faster, and that's coming from a stronger coordination between the lead and the surfactant there. Well, the same stronger coordination when we try to do the conversion from the intermediate phase using heat, using thermal annealing to convert into perovskite, that actually requires extra energy to overcome this coordination, and that slows down the crystallization for the perovskite crystal. So that's all are good. So you want faster nucleation and slower crystallization. And this process, we are able to observe it using our in situ UVVs. Okay, so that this is without surfactant and this is with surfactant. And we do a cutting at 550 nanometer, and that's what we see for both cases. Okay, a clearly much slower crystallization, which are preferred. Okay. I know I run out of time, but I just want to mention to you this multifunctional surfactant allow us to getting better crystallization orientation, and that will help the vertical transport. The evidence coming from two parts. One is for the normal XRD, the ratio between the 110 and this 112, the ratio, and this one is better, and this is 15.7, and this one is 10.3, and this one is only 7. This ratio tells us that you have better orientations here. And also from the grazing incident XRD, this part actually getting stronger, and we can see in the bulk perovskite, we get a better ordered out-of-plane orientation. And these two evidence tells us that we'll get a better crystal orientation, and that helps to improve the vertical transport. Okay, some passivation. This is the defect state passivation. We can getting it from the photoluminescence intensity and the transient photoluminescence lifetime. Actually, from the lifetime that's with our surfactant, you get a longer lifetime T2, which represents how the detrapping. So that indicates, yes, when we add it, we get less traps there. Okay. In short, that all the evidence here, including the FTIR, tells us the evidence of the lead and SO3 coordination. Okay. With that, we're almost in the end. Want to mention that by using that one, we have improved the VOC, and we have less higher electroluminescence quantum efficiency, that's corresponding to less non-radiative recombination, okay, which are all good. So for device, we are getting about 22.1% versus 19.3% for device for the small area, and for larger area, we can also keep it at a relatively good values there. So for this work, that is a comparison for the blade coated method, and we coat it at room temperature, and this is significantly better than the reported value of just above 21. We get 22.1. Okay, so with that, that's going to mention the protectivity of this multifunctional instability. You see that with 1.1% surfactant, you can see the protection of the perovskite film against the water is actually much better improved. Okay. And this tells you the stability under 80 degrees C, and this is the light stocking stability. In both way, adding this multifunctional surfactant give you a much improved stability. And actually, if you leave this one outside, you see that the one with surfactant give you much better stability. Well, if you do not surfactant, you'll see this one just go yellow, okay, with those hydrates there. Okay, I guess let me just show you briefly for fun, okay? Here is the ambient environment. Then how do we do a blade coating? That's a machine. That's the last slide. So we can, this part is a automatic drawdown machine, and we putting this one as a blade air knife. But this is a blade coating, and this one, when we put the perovskite and let this one go to do the coating, okay, to do the coating here. Just wait a little bit. Okay, almost done. Okay. After that, we can move our blade. And then here is our air knife. We blow with the angle, also blow of the perovskite film. You'll see this changes color, and our students will show you that how do you, when it's blow dry for a while, and then you will take a look of this one. It's a pretty uniform films here, okay? It's majority of this one, actually, this is a new process. So majority of the perovskite already converted, but we still leave it on 110 degrees for, you know, a short period of time. And then that will give you a film that's pretty uniform, shining film of perovskite. That's the things that we want to do printing. And we want to, this, I think it's a nice demonstration that we are able to do print perovskite solar cells. Well, now you can take it out. Be careful, 110 degrees C. That's hot, right? That's hot, right? Okay. Yes, this is the film that you can see, and this is the one that we can get a smooth film, and we put this is a photo that's with polyuse logo there. Okay, with that, let me get to the summary. Not really. We get two parts. When we talk about the perovskite organic solar cells there, the material development, what we learned from the old days, and how we apply those knowledge into the multi-component OPVs there. There are about different ways that it can actually play many methods to improve the device there. It's very exciting. We see 18% and even 19% reported. And organic semiconductors can help perovskite too. And the perovskite, I like the way that we can do in situ investigation for the perovskite solar cell, the film formation process, and that's lots of fun. And to give you, we can achieve 22% in the plate coating method, and we'll continue to do maybe larger and higher efficiency and stabler. That's always our goal to go. Okay, with that, I acknowledge the funding support from Hong Kong, from NSFC, from Shenzhen, and from PolyU. Okay. Including this endowed professorship fund. Okay, and with that, I thanks my students at the different stages there. They never really together. And here is my current small group, and we have people working in OPV. And this lady and this gentleman, we have people here now goes to US, Jin Sung Huang's group, and this is a professor now in Dr. Chen in Wuhan. And we have this a professor in Shenzhen, and we now have this energetic groups in Hong Kong that we are trying to do our best. And thank you all for your attention.
Okay, thank you very much. Since Professor Li has presented a very wonderful talk about his work in the past few decades, including two major parts. One is the organic semiconductor solar cells, and the other part is the perovskite. The two part is very hot field, and we can see that Professor Li also presented some comprehensive work in the past few years. Okay, now we have collected several and maybe a lot of questions from some platforms, and I will pick up some typical questions to Professor Li to answer the question. And the first question is about the morphology manipulation issue. As Professor Li mentioned in your not only the organic semiconductor solar cell or the perovskite, the morphology is a very important point. So I want to ask, have you considered how to control some condition to get some good uniformity or good morphology? Have there some general techniques to get a good morphology? Okay, this is the first question.
Well, it's actually a very broad question. Morphology in organic this polymer solar cells and the perovskite are kind of different, right? And in probably mention say polymer solar cells, then that's your solvent you use, your additive you use, and the addition, the condition you do the coating. And the third component, all related to the morphology. Okay, let's say the vapor pressure of, say boiling point and vapor pressure of the solvent. That's an important part for you to getting good film. Okay, the morphology are linked there. Okay, and some of the works that you, for example, many of the works that we do, say chloroform, it's a low boiling point. It's very easy to dry, and it's good for some systems to get high efficiency. Okay, but that part you have to think about how can you apply this one into say non-spin coating method. Okay, so that's the things I think the research field need to keep in mind on that one too. Okay, in general methods, then I would like to mention, say you have the different solvent vapor annealing, thermal annealing. You have additives, your solvent engineering, your mix the solvent, etc. Those are all the things that help you to fine tune. But unfortunately, majority of the time we are talking about the artwork rather than a very say systematic scientific research. And that part still need quite a bit of effort on that. Personally, I also start to look beyond the bulk heterojunction bulk heterojunction method. We also think about this sequential deposition type of the work, because I think that one might help you to give you more freedom to tune your morphology. Okay.
Okay, thank you, Professor.
Perovskite, I guess I'm not really expert on that, and we do lots of work according to literature and do our step-by-step work on that one. Okay, and some guidance on that. I think surfactant will help you somehow. So that the method of multifunctional surfactant, and which I think it's very promising in going forward.
Okay, thank you, Professor. And the next question is about in your first work you mentioned there are two the molecule packaging can. One is face on, the other is edge on. Yes, I want to ask what's the effect? What's the factor to infect the two different packaging cans? So what's the factor? Yeah, why they are so different? So yeah.
Oh, okay. Right. Okay. It's a very good question, and it's actually not easy. The work published in 2015. I can tell you that the work actually, the students actually started that one in 3 years before. So it's 2012 also. Okay. But we spent quite a bit of efforts try to understand it. The method of say the packing, molecular packing, right? Polymers or organic semiconductors, they like the in the pi stacking method direction is they do the best transport. Okay, so you don't want your say polymer, say for holes, you transport along this direction, and then you go to another donor material, you have to transport in the other direction. So that's disturbing it. Okay, so we think that's the way. Say if you have one material, you transport this much, another material stack on it, but it's still transporting in that direction. This will help you to do the overall transport. Well, my personal feeling on this one is this. Okay, we are in many of the times that our researchers are like, you say, semi-blind person. We are, touching a bigger elephant from different directions there. Okay, we can find some of the rules. That's part of the truth there, and that's already very excited. And then different people touching on different direction. Then we putting together, we get a more thorough understanding. In the ternary or multi-component solar cell research, this molecular compatibility is one important factor, I would say. And there are other methods too. Okay, other method or understanding mechanisms, including like alloy model, electron energy transfer, etc. of the model, etc. Okay. Well, I think we need to get an overall understanding from different. It's probably system and dependent too. Okay. So we should collect more information and try to get a unified understanding for this more and more complicated system for high efficiency.
Okay, thank you, Professor. Yeah, it's a very important question and need to be further studied. Yeah. Okay, the next question is about in the designing some molecule, some very important molecules. We want to ask why do you choose more deeper why what's the effect? So what's a critical role for the more deeper loom? Yeah.
Oh, okay. Very good question. Then it's starting with this. So you want to have us, because we're now starting from say actually a very good house now.
Yeah.
Okay. A very good house, because the material system, the binary system, is already give you pretty good efficiency. The high quantum efficiency, VOC loss probably not a big either, field factor good, etc. Right? And when you want to add more components, say help me to do absorption and help me to do transport, etc. This is more like a fine-tuning work. Okay, so why deeper HOMO? Okay, if I have a donor, and because my acceptor is fixed, okay, when adding a donor molecule, I don't want it to be shallower. Okay, how to say shallower HOMO, because it's this area, these two parts that determines the VOC. I don't want my adding component to reduce my VOC. So that's the part that when we design molecules, we keep in mind we want something to be deeper HOMO than our originally polymer for the binary system.
Okay, thank you, Professor. Okay, the next part is about your set work, perovskite. In one of your work, you say you're using the AFA, NFA to passivate the perovskite. I want to ask, what's the advantage of this material when compared to other material to passivate the perovskite?
Oh, okay. Good question. That's NFA. First, NFA so amazing coming from the design capability. Okay, it's you have so many variable you can do, and you can this one to try starting actually is because my new group started with OPV and perovskite together, and in our understanding of the perovskite, we see the passivation part. So some of the molecules with a specific bond will help you to do the passivation. Okay, and you say what's the advantage? Well, compared to the anti-solvent, pure anti-solvent, it definitely will help you to do some protection there. Okay, that's yes, we can do. It will passivate the traps and also improve the stability. And by this part, by themselves, it's already have the advantages there.
Okay, thank you, Professor. Okay, I think we have still a lot of questions, but due to the time limited, I will ask the last question to Professor Lee. And the last question is about your principal method to print the perovskite in your last part. The question is, they want to ask at the air direction and blue direction, what about the uniformity along the blue direction? Do you understand, Professor Lee?
Oh, no, below direction.
What's the uniformity for this direction material for this direction?
You mean the airflow?
The airflow, yeah.
What's
the uniformity along this direction? Yeah.
Well, this is engineering problem here. Okay, and in principle, there are different ways to solve it. Okay, first, in our case, the part you can see from the film that when we use air knife at a fast enough speed, we actually getting 10 centimeter is not an issue there. Okay, pretty uniform. Okay, we actually was asked by the reviewer to show something, so we take SEM for different parts of this 10 by 10 film. Then the SEM is uniform and optical is uniform too. Okay, and I want to point out that in reality, if you are designing a fabrication method, actually your system can have your air knife to be movable. Okay, not necessary to be fixed at the same position. And you can actually also use multiple if you want. Okay, so I think those are, the uniformity issue for the coating is not a problem at all.
Okay. Thank you, Professor. Okay, now I think we have taken 1.5 hours to this talk. We thank Professor Li very much. We thank Professor Li for the support to our journal. Yeah, Professor Hua Zhang. Yeah. Okay.
Thank you very much.
Thank you, Professor.
Okay, bye.
Okay, bye bye.
辛苦了，李刚，谢谢啊，时间太长了，抱歉。
不好意思。